September 5, 1977. Humanity launched a school bus-sized spacecraft carrying a golden record and 1970s computing power weaker than a modern car key fob. 48 years later, Voyager 1 is 15.4 billion miles from Earth, so far that sunlight takes over 22 hours to reach it, traveling at 38,000 miles per hour through a region no human-made object has ever touched. And in 2012, when it crossed the edge of our solar system's protective bubble, its instruments detected something impossible: plasma temperatures that suddenly jumped from 30,000 Kelvin to over 50,000 degrees, hotter than the surface of most stars. Here's the paradox: despite having less computing power than a 1980s calculator, despite being designed for a 4-year mission, Voyager 1 is still sending back data that's rewriting our understanding of where the solar system ends. How is it possible for 1970s technology to survive a cosmic boundary we didn't even know existed? And how much longer can we keep listening before the signal goes dark forever? The Voyager program wasn't supposed to make history. It was supposed to be a quick photo tour of Jupiter and Saturn. 4 years, 2 planets, mission complete. The official name wasn't even Voyager at first. It was the Mariner Jupiter-Saturn program, a modest follow-up to earlier planetary flybys. But then NASA's trajectory analysts noticed something extraordinary: the Grand Tour alignment. Once every 176 years, the outer planets align in a specific configuration that creates a gravitational highway. A spacecraft could visit all 4 giant planets, Jupiter, Saturn, Uranus, Neptune, using each planet's gravity to slingshot to the next, requiring far less fuel than direct flights. The window: 1977 to 1978. Miss it, and the next opportunity wouldn't come until 2153. Here's the counterintuitive detail: Voyager 1 was designed and built for a 4-year mission to Jupiter and Saturn. But engineers quietly overbuilt it: extra shielding, redundant systems, high-quality components, betting that if the Grand Tour became possible, the spacecraft might survive. They were told to design for 4 years. They built for forever. Voyager 1 lifted off from Cape Canaveral on September 5, 1977, 16 days after Voyager 2, which launched August 20, 1977, but on a faster trajectory, reaching Jupiter first. In March 1979, Voyager 1 encountered Jupiter, capturing the first detailed images of Jupiter's Great Red Spot and revealing it as a massive storm system. It discovered volcanic activity on Io, the first active volcanoes found beyond Earth, detected faint rings around Jupiter, and conducted close-up study of Europa's cracked ice surface, hinting at a subsurface ocean. That volcanic plume on Io was detected by accident when Voyager 1's navigation engineer Linda Morabito noticed a strange bump on the Moon's edge during trajectory analysis. It was a 300-kilometer-high eruption, proof that tiny moons could be geologically alive. In November 1980, Voyager 1 encountered Saturn, providing detailed imaging of Saturn's ring system and revealing thousands of individual ringlets. It discovered complex braided structure in the F-ring, conducted a close flyby of Titan revealing a thick nitrogen atmosphere, and discovered Saturn's magnetic field and magnetosphere structure. In February 1990, at Carl Sagan's request, Voyager 1 turned its camera back toward Earth from 3.7 billion miles away and captured the famous pale blue dot image, Earth as a tiny speck in a sunbeam. Immediately afterward, cameras were shut off permanently to conserve power. 3 things had to align perfectly for continued success: the Grand Tour window with its 176-year planetary alignment, radioisotope thermoelectric generators with 50-plus-year lifespans instead of solar panels that would fail beyond Mars, and deep space network upgrades that gave NASA massive radio dishes the sensitivity to hear whispers from the edge of the solar system. Any one of these missing, and Voyager dies in the outer planets. all three together. It reaches interstellar space. After Saturn, the twin Voyagers took very different paths, and discovered very different universes. In November 1980, after Saturn flyby, Voyager 1's trajectory bent sharply upward out of the ecliptic plane, the flat disk where planets orbit. Mission planners chose this route for a close pass of Titan, Saturn's mysterious moon. The cost: Voyager 1 would never visit Uranus or Neptune. The benefit: fastest route out of the solar system, straight toward interstellar space. Voyager 2 continued the grand tour. After Saturn in August 1981, it flew past Uranus in January 1986, the only spacecraft ever to visit, discovering 10 new moons and a tilted magnetic field, and Neptune in August 1989, the only spacecraft ever to visit, discovering the Great Dark Spot, active weather systems, and geysers on Triton. Voyager 2 became the only spacecraft to visit all 4 giant planets. But Voyager 1 became the fastest object humanity ever sent into deep space, and the first to leave the solar system entirely. As of 2025, Voyager 1 is 15.4 billion miles from Earth, $164, traveling at 38,000 miles per hour relative to the Sun. Voyager 2 is 12.8 billion miles from Earth, $137, traveling at 34,000 miles per hour. Voyager 1 is 164 times farther from the Sun than Earth is. That may not seem like much when you're used to talking about light years. But imagine this: you're standing in New York City. Someone in Los Angeles, 2,800 miles away, whispers something. You hear it 22 hours later. That's the communication delay with Voyager 1. Every command sent from Earth takes 22.5 hours to arrive. Every response takes another 22.5 hours to return. Total round trip, 45 hours. If engineers notice a problem today, the earliest they can confirm a fix worked is the day after tomorrow. And it's getting worse. Voyager 1 is moving away at 38,000 miles per hour, about 330 million miles per year. Every year, the delay grows by 30 minutes. What Voyager 2 achieved that Voyager 1 didn't: complete the grand tour, the only spacecraft ever to visit Uranus and Neptune. What Voyager 1 achieved that Voyager 2 didn't: first object to enter interstellar space, August 25, 2012. And that crossing revealed something no one predicted. To understand what Voyager 1 discovered, you need to know 2 terms that are constantly confused: the heliosphere and the heliopause. The heliosphere is like a giant bubble of charged particles blown outward by the Sun. The Sun doesn't just emit light. It emits a constant stream of charged particles, mostly electrons and protons, called the solar wind. This wind rushes outward at roughly 1 million miles per hour, creating a protective bubble around the entire solar system. Think of the heliosphere as the Sun's atmosphere, except it extends billions of miles into space, far beyond the planets. Inside this bubble, solar wind dominates. Particles from the Sun, magnetic fields from the Sun. The Sun's influence. The heliopause is the edge of that bubble, the boundary where the solar wind finally stops. Beyond the heliopause lies interstellar space, the region between stars, filled with the interstellar medium, gas, dust, cosmic rays, and magnetic fields from distant stars and ancient supernovae. Think of the heliopause as the shoreline where the river of solar wind meets the ocean of interstellar space. If the heliosphere is a ship's wake spreading behind it as it moves through water, the heliopause is where that wake finally dissipates and blends into the surrounding ocean. On August 25, 2012, Voyager 1's plasma wave instrument detected a sudden, dramatic change. For months, Plasma density had been slowly rising as Voyager approached the boundary. Then, on August 25, it jumped by a factor of 40 in a matter of days. Simultaneously, galactic cosmic rays from outside the solar system surged, solar particles from inside the heliosphere dropped to near zero, and magnetic field direction remained steady but intensified. Voyager 1 had crossed the heliopause. It was no longer in the solar system. It was in interstellar space. For the first time, humanity had direct measurements of the interstellar medium, the ocean our solar system swims through. And the data was shocking. The timeline: 1977 launch, 1979 to 1980 Jupiter and Saturn flybys with primary mission complete, 1990 pale blue dot photo with cameras shut off, 1998 Voyager 1 overtakes Pioneer 10 as the most distant human-made object, 2004 Voyager 1 crosses termination shock where solar wind slows from supersonic to subsonic at about 94 Australian dollars, 2007 to 2010 Voyager 1 passes through helio sheath, the turbulent boundary region between termination shock and heliopause, 2012 Voyager 1 crosses heliopause at 121 Australian dollars entering interstellar space, and 2018 Voyager 2 crosses heliopause at 119 Australian dollars. From termination shock to heliopause, 8 years to cross a turbulent no-man's land. From heliopause to today, 13 years into interstellar space, and still going. Let's restate the core mystery. How do you communicate with a 1970s spacecraft 15.4 billion miles away, using a transmitter weaker than a refrigerator light bulb? The answer is one of the most astonishing feats of engineering ever attempted. Voyager 1's main radio transmitter outputs 23 watts of power. For comparison, your smartphone charger uses 20 watts, an old incandescent light bulb uses 60 watts, and your microwave uses 1000 watts. Voyager's transmitter is weaker than a nightlight. And it's trying to send a signal across 15.4 billion miles. Let's follow a single radio signal from Voyager 1 back to Earth. Radio signals travel at the speed of light, 186,000 miles per second. From New York to Los Angeles, 2,800 miles, a radio signal arrives in 0.015 seconds, 15 thousandths of a second, essentially instant. From Earth to the Moon, 238,000 miles, a radio signal takes 1.28 seconds. When astronauts on the Moon spoke to Mission Control, there was a 2.5-second delay for round-trip communication. From Voyager 1 to Earth, 15.4 billion miles, a radio signal takes 22.5 hours. If Voyager detects something right now, NASA won't know for nearly a full day. Radio signals spread out as they travel, following the inverse square law. When Voyager transmits, its 23-watt signal spreads out in all directions, though focused somewhat by the dish antenna. By the time that signal reaches Earth, it has spread across a sphere 15.4 billion miles in radius. The power that actually reaches Earth? 10 to the power of -16 watts. That's 0.0000000000000001 watts. 1/10 quadrillionth of a watt. To put that in perspective, the energy Voyager's signal delivers to Earth's receivers in one day is less than the energy released by a single snowflake hitting the ground. To catch that unimaginably faint whisper, NASA uses the Deep Space Network, 3 massive radio antenna complexes spaced around the globe. Each complex has multiple dishes, but the largest are the 70-meter antennas, giants the size of a 20-story building. A 70-meter dish has a collecting area of roughly 3,848 square meters. For comparison, that's about half a football field of radio collecting surface, all focused on a single receiver. Even with that enormous dish, Voyager's signal is still so faint that the DSN uses ultra-low noise amplifiers cooled to near absolute zero, about -270 degrees Celsius, to reduce thermal noise that would otherwise drown out the signal. Because Earth rotates, a single antenna complex can only see Voyager for part of the day. That's why NASA built 3 complexes spaced roughly 120 degrees apart in longitude: Goldstone, California; Madrid, Spain; and Canberra, Australia. As Earth spins, one complex sets below the horizon relative to Voyager's position in the sky, but another rises above it. Together, they provide continuous coverage, 24 hours a day, 365 days a year. If any one of these sites went offline permanently, we'd lose contact with Voyager for 8 hours every day. Critical data could be lost. Commands could miss their transmission windows. The DSN isn't just receiving Voyager's signal. It's the only thing standing between Voyager and eternal silence. Here's the problem: there's no way to recharge Voyager. Solar panels, the obvious solution for most spacecraft, don't work. By the time Voyager crossed Jupiter's orbit, sunlight was already 25 times weaker than at Earth. At its current distance, sunlight is 27,000 times weaker than on Earth. Solar panels would be useless. Voyager runs on radioisotope thermoelectric generators, 3 cylindrical units mounted on a boom extending from the spacecraft body. Inside each RTG, plutonium-238. Plutonium-238 decays naturally, releasing heat. Thermocouples surrounding the plutonium convert that heat into electricity. No moving parts. No sunlight required. Just radioactive decay, slow, steady, unstoppable. At launch in 1977, the 3 RTGs together produced 470 watts of electrical power. In 2025, 48 years later, the RTGs produce approximately 220 watts, less than half the original output. Why the drop? Plutonium-238 has a half-life of 87.7 years. After 48 years, a significant fraction has decayed into non-radioactive elements, producing less heat. Additionally, the thermocouples themselves degrade over time, becoming less efficient at converting heat to electricity. To stretch every watt, mission engineers have systematically shut down non-essential systems. In 1990, cameras shut off after the pale blue dot photo. In 1998, the ultraviolet spectrometer powered down. In 2007, the plasma science instrument heater turned off, the instrument froze but remained functional. In 2016, trajectory correction thrusters retired and backups activated for the first time in 37 years. In 2019, some science instrument heaters turned off. In 2020, the cosmic ray instrument partially powered down. Currently active systems as of 2025 include the high-gain antenna and radio transmitter, attitude control that keeps antenna pointed at Earth, for science instruments, magnetometer, plasma wave sensor, cosmic ray detector, low-energy charged particle detector, and the command and data system on-board computer. On February 14, 1990, at Carl Sagan's urging, Voyager 1 turned its camera around one last time and photographed Earth from 3.7 billion miles away. A pale blue dot, barely visible, suspended in a beam of scattered sunlight. It's one of the most iconic images in history. And then the cameras were shut off. Permanently. Not because they broke. Because the spacecraft needed the power more than it needed eyes. Voyager 1 has been blind for 35 years. Today, Voyager 1 does only the essentials: collect data from 4 remaining instruments, compress and store data in onboard memory, transmit data back to Earth at 160 bits per second, about 1,000 times slower than a 1990s dial-up modem, listen for commands, and keep the antenna pointed at Earth. That's it. No photos. No maneuvers. No experiments beyond what the 4 instruments passively detect. Current power estimates: 2025 about 220 watts available, 2030 about 200 watts will require shutting down one more science instrument, 2036 power drops below minimum needed to operate any science instruments and transmit data. At that point, Voyager 1 goes silent. Not dead, its computers may still run for years on residual power, but unable to talk to us. The mission ends not with a shutdown command, but with a slow fade into static. Voyager 1 has survived nearly 5 decades in one of the harshest environments imaginable. But it hasn't been smooth. In 2017, engineers noticed that Voyager 1's attitude control thrusters, tiny nozzles that fire to keep the antenna pointed precisely at Earth, were degrading. The thrusters were clogging with silicon dioxide residue from decades of use. If the antenna drifts even a fraction of a degree off target, Earth loses the signal. Permanently. With Voyager 15.4 billion miles away, there's no way to recover from a lost lock. The spacecraft would tumble silently through interstellar space, data streaming into the void. Voyager has backup thrusters, a secondary set used only during planetary flybys for trajectory corrections. They hadn't fired since 1980. 37 years dormant. Engineers weren't sure they'd still work. On November 28, 2017, engineers sent the command to fire the backup thrusters. 22.5 hours later, telemetry confirmed, they worked. The backup thrusters fired perfectly, oriented the spacecraft, and took over attitude control duties. Voyager 1 got a new lease on life, likely extending operations by 2 to 3 years. In May 2022, Voyager 1's telemetry data suddenly became garbled. The spacecraft's attitude articulation and control system, which reports the spacecraft's orientation, started sending back nonsensical readouts. The spacecraft was clearly still functioning, signal strength was normal, antenna pointing was correct, but the data looked random, like the onboard computer was confused about where it was. Engineers spent months trying to diagnose the problem remotely. Remember, every troubleshooting command takes 45 hours for a round-trip answer. Testing a single hypothesis could take a week. They checked memory corruption, unlikely because redundant systems showed same issue, cosmic ray strike, possible but didn't match patterns, and software glitch, most likely. In August 2022, engineers traced the issue to a single faulty chip in the AACS computer. The AACS had somehow started routing telemetry data through a corrupted memory location before sending it to Earth. The fix: send a command instructing the AACS to use a different memory location, essentially a workaround that bypassed the corrupted chip. The command worked. Telemetry returned to normal. But it was a stark reminder: Voyager's computers are 48 years old, using 1970s-era components. They're degrading. And every fix is a patch on top of patches, stretching the spacecraft beyond anything its designers imagined. By 2030, RTG power output will drop below 200 watts. Voyager will face a critical choice: which instrument to shut down next. Current candidates for shutdown include the magnetometer that measures magnetic fields, low-energy charged particle detector, and cosmic ray detector. Each instrument provides unique data about interstellar space. Losing any of them reduces our window into this unexplored frontier. Engineers are planning a staged shutdown sequence that prioritizes the most scientifically valuable instruments. The plasma wave instrument, which detected the Heliopause crossing and measures the density and properties of interstellar plasma, will likely stay on until the very end. The cosmic ray detector may be the first to go, since its data overlaps somewhat with other instruments. If the staged shutdown is managed carefully, Voyager 1 could continue transmitting science data until approximately 2036, giving us another decade of interstellar measurements. After that, power will drop too low to run the transmitter. Voyager 1 will go silent. The end is coming. Not suddenly, but inevitably. Voyager 1 is fighting on multiple fronts: power decay with RTGs losing about 4 watts per year, component aging with 48-year-old electronics operating far beyond design life, distance with signal delay now 22.5 hours and growing by 30 minutes every year, and data rate limits at 160 bits per second, so slow that a single smartphone photo would take 8 hours to transmit. Every year, the mission gets harder. Based on current power projections, Voyager 1 will likely cease science operations in 2036. That's 11 years from now. Voyager 1 launched in 1977. It will operate until approximately 2036. 59 years of continuous operation. A spacecraft designed for 4 years will have lasted nearly 15 times longer than planned. 2036 is the optimistic estimate, assuming no critical component failures, successful staged instrument shutdowns, and continued DSN support. But a single catastrophic failure, a computer crash, a memory corruption that can't be bypassed, a thruster clog that can't be cleared, could end the mission tomorrow. At most, we have 11 years. Possibly less. One day, maybe in 2036, maybe sooner, engineers at the Deep Space Network will receive the last coherent signal from Voyager 1. They may not know it's the last one. There will be no final message, no goodbye. Just a slow fade as the signal weakens, breaks apart into noise, and finally vanishes. After that, Voyager 1 will still be out there, tumbling silently through interstellar space at 38,000 miles per hour. But we'll never hear from it again. Voyager 1 launched on September 5, 1977. The mission was designed to last 4 years, until 1981. As of 2025, it has been operating for 48 years, 12 times longer than planned. If it reaches 2036, it will have lasted 59 years, nearly 15 times its design life. When Voyager launched, its computers had 69.63 kilobytes of memory, less than a single email, and 8,000 instructions per second processing speed. For comparison, a modern smartphone has 8 to 12 gigabytes of RAM, roughly 115,000 times more memory than Voyager, and billions of instructions per second, over 100,000 times faster. Your phone is 100,000 times more powerful than the computer navigating interstellar space. The furthest human-made object in existence. The first spacecraft to enter interstellar space. The only active probe measuring the boundary between the Sun's domain and the galaxy beyond. And it's powered by 1970s technology that can't run a web browser. Voyager 1 will continue traveling through interstellar space long after we lose contact. In about 300 years, it will pass beyond the Oort cloud, the outermost edge of the Sun's gravitational influence. In 40,000 years, it will drift within 1.6 light-years of the star AC plus 793888 in the constellation Camelopardalis. In millions of years, it will still be wandering the Milky Way, carrying its golden record, a message in a bottle from a species that once looked up at the stars and wondered. Voyager 1 is no longer just a spacecraft. It's a monument. A time capsule. And a reminder that even the quietest signals, sent from the smallest voices, can echo across the universe.